Integrated rate laws. Integrated rate laws are the application of calculus to the rate equations we have learned for simple order relationships. Let's look at the simple first order reaction A gives B. We can express the rate law in terms of the reactant A in this way: minus the rate, the change in concentration of A over the change in time, equals K, the rate constant, times the concentration of A. This is the instantaneous rate, not the average rate. The lowercase d is used in calculus for the change instead of using the delta. This equation can be rearranged to this form: the change in concentration of A over the concentration of A equals minus K times the change in time. Integrating the equation produces this equation: natural log of the concentration of A at time t equals minus K times the time t plus a constant C. When the time is 0 at the start of the reaction, substituting that value for t gives us the value of the constant C, which is equal to the natural log of the concentration of A at time 0, that is, the initial concentration of A. Those who have had calculus should recognize the integral form and what the results of the integration are. For those who have not had calculus, or who don't remember, the important thing is the final equation, which is natural log of the concentration of A at time t, square brackets around A sub t, equals minus K times t plus the natural log of the initial concentration of A, square brackets around A sub 0. The equation log of A sub t equals minus kt plus log of A sub 0 has the same general form as any linear equation, y equals mx plus b, if y is the natural log of the concentration instead of the concentration itself. This means that a graph of the natural log of the concentration versus time will give a straight line plot if the reaction is a first order reaction. In that case, the slope of the line is minus K, minus the rate constant, and the intercept of the line is the natural log of the initial concentration of A. This can be a very useful tool. If we have the concentration of the reactant as the reaction proceeds, and plotting the natural log of that concentration versus time gives a straight line, then the reaction is a first order reaction. So plotting natural log of concentration versus time can show us it is a first order reaction without doing a lot of experiments with initial rates. In addition, if it is a first order equation, we can determine the value of the rate constant from the slope of the line, rather than by doing initial rate experiments. We can rearrange the equation into a sometimes more useful form, which separates the concentrations from K and T. By subtracting the natural log of the concentration of A0 from both sides, we move the concentrations to the left side of the equation, producing the equation natural log of the concentration of A at time t minus the natural log of the initial concentration of A equals minus kt. Remembering that the difference between the logs of numbers is the log of the ratio of the numbers, this becomes natural log of the ratio of the concentration of A at time t over the initial concentration of A equals minus kt. This equation allows us to do several things. It allows us to determine the rate constant from the initial concentration and the concentration at another time t. Or it can allow us to determine the concentration at some time t if we know the rate constant and the initial concentration. or it can allow us to determine how long the reaction has been running if we know the initial concentration and some later concentration, and the rate constant. A comparison to the rate law expression shows that we can use the rate law expression to determine the value of the rate constant, once we know the order of the reaction, or to find the value of the initial rate with different concentrations. But we cannot look at how the concentrations change with time for a single reaction. On the other hand, the integrated rate law allows us to look at the time dependence of the concentration or determine the rate constant. But the order of the reaction is already known before we can use the integrated rate law. Let's consider the reaction for the conversion of methyl isonitrile into acetonitrile. CH3NC goes to CH3CN. We conduct this reaction in a closed, sealed container at a constant temperature. Here is a graph of the partial pressure of methyl isonitrile in the container as a function of time. This data was collected for this reaction at a temperature between the boiling point of methyl isonitrile, 60 degrees Celsius, and the boiling point of acetonitrile, 82 degrees Celsius. This temperature was chosen so that the methyl isonitrile would be a gas, and once the acetonitrile was formed, it would be a liquid, exerting some vapor pressure. If we know the vapor pressure of the acetonitrile at that particular temperature, we can determine the partial pressure of the methyl isonitrile by measuring the total pressure and subtracting the vapor pressure of acetonitrile. When we plot the natural log of the pressure of CH3NC versus time, we get a straight line, which means that the process is a first-order process. The rate constant K is the negative of the slope of the line for the graph on the right, which we determined to be 5.1 times 10 to the minus fifth per second. One of the most useful parts of the integrated rate law is the half-life. The half-life is defined as the time required for 1/2 of a reactant to react. The symbol used for half-life is T sub 1/2. At the time of the half-life, the concentration of A is half what it was at the beginning of the half-life. Or, concentration of A at the half-life equals 0.5 times the initial concentration of A. We can plug these values into the integrated rate equation for a first-order process and get the natural log of 0.5 times the initial concentration of A over the initial concentration of A equals minus K times T sub 1/2, that is, the half-life. This simplifies to natural log of 0.5 equals K times the half-life. The natural log of 0.5 is minus 0.693, so this becomes minus 0.693 equals minus K times the half-life, and 0.693 over K equals the half-life. Since there is no concentration shown in this last equation, this means that for a first-order reaction, the half-life does not depend on the initial concentration of the reactant. It also means that we can determine the half-life if we know the rate constant, and the rate constant if we know the half-life. This is extremely useful, particularly when we are dealing with radioactive decay, which is a first-order process. We can use this to determine the age of a sample with a known initial amount of a particular radioactive isotope, which is how carbon dating works. There are two problems using the integrated rate law and half-life on the problem sheet for this lesson. Second-order processes. For a reaction that is second order in a single reactant, other types of second order reactions are more complicated. The rate law expression is minus the change in concentration of A over the change in time equals K times the concentration of A squared. If we rearrange this, as we did for the first order expression, to bring the concentration terms together and alone, we get the equation minus change in concentration of A over the concentration of A squared equals K times the change in time. When we integrate this, we get 1 over the concentration of A equals KT plus C. When we substitute times 0, we get that the constant is 1 over A sub 0, that is the initial concentration. So the reaction becomes 1 over the concentration of A at time t equals K times T plus 1 over the initial concentration of A. This also has the form of a linear equation, with y equal to 1 over the concentration of A. So, if we plot 1 over the concentration of A versus time, we will get a straight line if the reaction is second order. The slope of the line is K, the rate constant, and the y-intercept is 1 over the initial concentration of A. Let's look at an example of this. The reaction for the decomposition of NO2 gives NO plus 1/2 O2, is a second order reaction in NO2. We collect data for the concentration of NO2 at 300 degrees Celsius, which are shown in this table. If we calculate the natural log of the concentration and plot the natural log of the concentration of NO2 versus time, we do not get a straight line, which means that the data are not for a first order reaction in the concentration of NO2. If, on the other hand, we calculate 1 over the concentration data and plot 1 over the concentration of NO2 versus time, we do get a straight line. So the data are for a second order reaction in NO2. What does the half-life look like for a second order process? Once again, the concentration of A at the half-life time is half the initial concentration of A. This gives us the relationship 1 over 0.5 times the initial concentration of A equals K times the half-life plus 1 over the initial concentration of A. 1 over 0.5 times the initial concentration of A is 2 over the initial concentration of A. And when we move the two concentration terms to the left side, we get 1 over the initial concentration of A equals K times the half-life. When we solve for the half-life, we get 1 over the product of the initial concentration and the rate constant equals the half-life. This means that for second-order reactions, the half-life is dependent on the initial concentration of the reactant. For this reason, the half-life of a second-order or higher reaction is not a particularly useful number, since any change in the concentration of the reactant will change the half-life of the reaction.